So yesterday we started with memory management unit, which is a hardware part, whose main goal is to map the virtual addresses to the physical addresses. So this is one of the important thing, and so many algorithms are used for that purpose. But the simplest method is with the relocation register. Okay, we already saw the address binding, like compile time, then load time, then execution time. So at different time context, there is an address binding, and this address binding will map the addresses from one representation to other representation. So if programmer is making use of symbolic addresses, and actually instruction or data will be in the main memory, that is at the physical address, in between these so many bindings happen. Okay, so this part we already covered yesterday. Now let us see the dynamic relocation using the relocation register. Okay, so what happens is, whatever your function is there, whatever your routine is there, it will be not loaded until it is called. Okay, so this offers to a better memory space utilization. Reason behind that is, for example, if the program is bigger, say for example it is bigger than your memory size. Okay, that is one thing. Or maybe for example 10 KB program is there, but because of branching, say for example, if the condition is true, do this and this, otherwise do that and that. Now depending upon whether that condition is true or not. Say for example, if age is less than 18, we want to perform some sort of things, otherwise we want to do something else, right? So it is guaranteed that either if part will be executed or else part will be executed, and that depends on the condition, right? And for that reason, maybe one routine is there for if condition is true, and if it is false, some other routine is there. So routines will not be loaded into the memory until it is called. Now when that routine will be called is very simple thing. If the condition is true, routine 1 will be called. If the condition is false, routine 2 will be called, right? And that is the reason routines will not be loaded, and that results in memory space utilization. The routines that are not called will not be loaded into the memory. Okay, so that results in space utilization, rather I can say memory space utilization, right? But remember, whenever you want to call the routine, in order to make its loading fast in the memory, routine should be on the disk in relocatable format. Yeah, that is what our object codes are there. Yesterday I was talking about obj dump, that is the utility. Even nm is also one more command used on Linux and Mac OS Unix. That gives you the in-depth details of the object code, even executable code also. As it is not ASCII, these programs will help you to get those details. Okay. As I already mentioned, this will be useful when large amount of code are needed to handle infrequently occurring cases. Just I mentioned, see, if 90% of the time if condition is true and else code is not at all required, so that is basically called as infrequently occurring cases. Okay, so frequently required code will be in memory, and those things which are infrequent will not be in memory, but they will be on disk in relocatable format. With this approach, basically we don't require any support from operating system. This can be easily implemented by means of some sort of relocation register, where it will simply add whatever the logical address is there into the relocation register. That's it. Okay, and that results in the physical address, and then memory access will be initiated by the operating system. So that is how how it works with the relocation register. Now about dynamic linking specifically, where most of the time in Windows platform, this is typically called as DLL, Dynamic Link Library. It is called as a DLL, but in Linux it is called as a shared code. Now let me tell you what is shared code. First of all, you assume that there is an application, some graphical user interface is there, graphical application is there. You imagine something like you have a notepad, you have a calculator, you have a calendar. So many applications are there, and in these applications there are some common components. Like we have labels, we have text boxes, we have buttons, we have radio buttons, check boxes. These are all GUI components, right? Now, if multiple applications are rendering these GUI components using any of the programming language, doesn't matter, a native support from operating system is required in order to render it on your screen. Of course, within the area of that application. And for that purpose, if we need a separate code in every application, what will happen is it results in a huge size of your application. One of the simplest solution is the shared libraries, or also called as a dynamic linking. What happens in that case is, say for example, code required in order to render the button. We have OK button, save button, cancel button, right? So whatever the code required to render that button will be a part of operating system, and it is already there in the memory, right? Now, whenever your application calls some sort of function, something like make button or a new button, something like that. In case of Java, could be something like java.awt.button, something like that, right? So what happens is the code which is already in the memory will be dynamically linked. It's not static linking, because static linking we studied. Simplest example I have given, say square root function from math.h. Okay. Now whenever I compile my code, the math.h object code plus my program's object code statically linked together. So that will be available in the single binary program image. That is not the case with dynamic linking. Dynamic linking, it is like code server kind of a thing. Okay. So DLL servers are there and they are already there in the memory. Whenever any application needs to use that code, that will be dynamically linked with your code. And how that happens is by making use of some sort of piece of code called as stub. I just highlighted that on the slide, stub. Okay. So exactly what happens in dynamic linking is postponed until execution time. That means whenever you are calling any function, it will just have small piece of code, kind of a pointer, kind of a stub. This is called as actually stub. Okay, and that is used to locate the actual address in the memory for that library routine. So for example, whatever code is required for rendering the button will be in the memory at some specific address, and that address is not known to my application. So what my application does is that part, or rather operating system will replace that with some small piece of code, and this small piece of code will replace itself with the address of routine. And once actual address from that memory is available, that is the physical or absolute address, then that code will start its execution. Okay. Now it is responsibility of operating system to check if the routine is in processor's memory address, right? If not in address space, then add it to the address space. That's it. So this dynamic linking is really helpful in order to make your executables smaller in size. Whenever we build libraries, say when we say math library, when we say graphics library, okay. So in order to implement these kind of libraries, this dynamic linking is used. This, as I already mentioned, this is also called as shared libraries. On Unix and Linux, usually they will have the extension something called as .so. .so, where .s stands for shared, O stands for object. .so, shared object, that is your shared libraries. Now, sometimes what happens is whenever we modify the version are there, I modified my library with some additional features, okay, and there are still applications they are making use of. How to deal with this? The solution to this could be versioning. So for example, if library, say libgraphics is name of my library, lib graphics, and previous version was 1.3. Now I updated it to 1.4, but there are still applications with 1.3. Okay, so both the libraries will be in the memory, libgraphics 1.3 and libgraphics 1.4. And when there are no applications making use of 1.3, then and then only that will be removed from the memory. So library versioning is most of the time used. So this is called as dynamic linking. Now one more concept is there called as a swapping. Those who have already installed Linux operating system, they may have come across something like swap partition. So usually in installation we create three partitions. One is called as a root partition, one is called as boot partition, and one is swap partition. Now whatever this swap partition is there, that is called as a swap space. That is also called as a backing store. Okay. So what happens, rather I can say what is use of this is very simple. Whenever memory is full, say for example 20, 25 applications are running there and memory is full, and now I want to start one more application, but there is no space in the memory, then operating system has to select maybe waiting processes or processes with lower priorities, or maybe the jobs running in background. Such processes will be selected to remove temporarily from memory to backing store. Okay. Now this backing store is nothing but the swap space. So even in case of a Windows operating system, if you go to the properties of any drive, say C drive or D drive, and you will find there something called as a virtual memory, and something like 10% or 15% of the space of your disk will be used as a virtual memory. So remember, it is the swapping area. It is the backing store. Okay, Linux or Unix makes use of separate partition for that. Windows try to utilize from existing whatever the partitions you have created. Okay, one of this is we can have, or even processes can exceed the memory space, physical memory. So even though my memory is say 2 GB, I can have processes that needs more than 2 GB. Okay, so that is basically called as a swapping. Now what is backing store? This is a fast disk large enough to accommodate copies of all memory images for all users. So two requirements are mentioned there. It should be fast. Okay, that is actually a problem with Windows, because Windows go with NTFS, right? Whereas in case of Linux, because this is a separate partition, a separate file system will be there, and that is not usable area by the users, right? So to make it fast, this plays important role with the file system. So that is one thing, fast, and it should be large enough to accommodate copies of all memory images. Copy of all memory images means all the processes from all the users, and that is the reason in Linux the recommendation is the swap partition should be 2 times of your RAM, because memory image of all processes, definitely they are utilizing some sort of RAM. So if my backing store is 2 times of that, definitely it will accommodate all the copies of all the processes of all the users. Right? So that is the backing store. Now roll out and roll in, also called as swap out and swap in. So swapping variant used for priority based scheduling algorithm. If it is priority based, lower priority processes are basically swapped out, so higher priority processes can be loaded and executed from memory. Remember, the generic concept is called as a swap out, swap in. That means temporarily taking out the memory required by that process to backing store. That is called as a swap out. Okay. Whereas again brought back into the memory, the process will be brought back into the memory for continued execution is called as swap in. But if the priority based scheduling algorithms are used, swap out is called as roll out and swap in is called as a roll in. Just different names are there, concepts are same, because this the question can be asked. Most of the time this question happens in case of GATE exams. Currently running process is finished successfully, that is terminated, with space in the memory. Now what are the processes that we want to take into the memory? For that purpose we need to take ready processes. Voice is breaking. Let me check it. Hello. Okay, so let us continue. Actually, there is college internet, so I just switched to mobile. So let us continue. So whenever I was just talking about whenever there is space in the main memory because few processes have completed successfully, then whatever the processes on the backing store, that is on the swap space, needs to be taken into the main memory. And for that, operating system maintains a ready queue of ready to run processes which have memory images on disk. Try to understand ready queue is there for ready processes for memory, in memory processes also. Similarly, the processes that are ready to run but not in the main memory. So separate ready queue is there so that whenever there is a space in the main memory, such processes will be brought into the main memory. Otherwise, what will happen is
Sir, you are not audible, sir.
hello. Am I audible? Hello. Am I audible? Yes. Okay. So let us continue. So by default, the swapping is disabled, but and this threshold of memory could be something like 80% or something like that. So that has to be decided by the operating system. And whenever demand for memory is again reduced below that threshold, so that will be as percent of the memory. So for example, if it is 2 GB, so 80% is 1.6 GB. So initially, swapping is disabled. Being allocated part of memory and it reaches the threshold, say 80%, swapping will be enabled. Okay, so processes may be swapped out, swapped in depending upon the dynamics of how processes are occurring in the system. And after demand is reduced, say for example, it goes below the threshold, swapping will be disabled. That is how swapping begins. Now this is the schematic view of swapping. The main thing is that lower part of main memory is utilized by operating system. Remaining part is considered as a user space, and there will be so many processes into the user space. Now we have a separate backing store, that is the swap area. The operation swap out is given there, which will transfer process P2 from backing store to the user space. Now that is how it works. So this is a schematic view of the concept swapping. Now for context switching, we need to calculate the time required for context switch, which includes the operation of swapping. So for example, process P2 is selected by the scheduler, but it is not available in the main memory. That means such process need to swap in. And in order to swap in that process, maybe because of memory restriction, you need to swap out some other process. Okay. So in that case, context switch time can be very, very high. One small example is given here. Suppose 100 MB process is there, swapping to hard disk with transfer rate of 50 MB per second. 50 MB per second. So size of process is 100 MB. So swap out time, definitely it is 2000 milliseconds. Okay. Plus swap in of same size process. That means, say example, P1 will be swapped out to make space for P2, and P2 will be then swapped in. So the time required to swap out P1 is 2000 milliseconds. Time required to swap in P2, that is 2000 milliseconds. So that results in 4 seconds. Remember, that results in 4 seconds. So this can be reduced if reduced size of memory is swapped. Okay. So of course, for that you should know how much memory is really being used, and for that Linux and Unix support some sort of system calls request memory and release memory. The key point here is whenever swapping is included in the context switch, the time required for context switching is very, very high. Okay, so that is the main thing here. Not only this, but there are few other constraints also there. For example, if pending IO is there, operating system cannot swap out as IO would occur to wrong process. Remember, if one process is waiting for some sort of input output and that has initiated the IO, and such processes is swapped out once IO is finished, okay, that may occur at wrong process if another process is located at that address space, right? Or else there is another solution known as double buffering, with always transfer IO to kernel space and then from kernel space to the IO device. But because of this double copy, this approach adds overhead to the operating system. Okay. So most of the time this standard swapping is not used in most of the modern operating system, but modified versions are more common, where swap only when free memory is extremely low. That means whatever the threshold we talked about, keep that threshold high enough so that whenever memory is extremely low, then and then only make use of swapping. Now swapping on mobile systems, typically it is not supported. Mobile system mainly make use of flash memory based. So there is a small amount of space and a limited number of write cycles. So why it is not supported, reason behind that is it will definitely result in poor throughput. Okay. Instead of that, other methods will be used here. For example, in case of iOS, the apps will be asked voluntarily to relinquish the allocated memory. Even there are certain applications available there, something like free memory or something like that, wherein if you execute that, maybe few apps will be simply removed from the memory, right? Wherein the same thing I mentioned, Android. In case of Android will terminate the app if low free memory is there. So it first write the application state to the flash for fast restart. So whenever such application is again coming from background into the foreground, that will be restarted very, very fast. Okay. Swapping is mostly not used on mobile systems, but there is something called as a paging. That system will be used. Anyways, we'll see paging later on. That is part of this unit also. So paging is also required. So that is being used by most of the mobile operating systems. Now next part is contiguous allocation, but I think we'll stop here right now. So if you have any doubt, please ask. Let me stop the recording.